All right, Abby, I'm ready when you are.
Okay, I'm ready.
Yay. Okay. So we are learning about waves this week. So we're going to go over an overview of waves and then we're going to have a chance to practice. And then, hi, Madeline, perfect timing. So we are going to go ahead and get started on waves. Like you are going to read this week, there are different characteristics and different types of waves. And then there are calculations in finding out the wavelength, the speed, and the frequency for each one. So we're going to learn some key vocab words. We're going to learn some big information. So if you don't already have something out to write some things down, I don't have a worksheet for you to be filling out. However, I do have some important information. I'll tell you what I want you to jot down, okay? So let's go ahead and get started. So we are talking about waves. Waves are probably one of my personal favorite things to teach because I think that they're really, really cool and interesting. So we often think of waves that we know about the wave at games in the crowds. We think about waves when we think of ocean waves. We think about sound waves when there's an earthquake that sends out seismic waves. And then there is this thing called light waves, which is what we see as light. So whenever we see a color, when we see visible light, it's actually a specific wave, a wavelength, right? So in general, what we think about a wave is a repeating disturbance that transfers energy through matter or space. So really important for us to kind of get that, right? Really important for us to realize that specifically waves transfer energy. Waves are energy. So a lot of the time we can think even in our own bodies, right? We know that I was just got off a lesson teaching about cellular respiration and how that brings us energy that we need to use for ourselves. Things like talking. When we talk, it takes a lot of energy. And we are releasing that energy into the air, into the medium in which that sound is going to travel. Remember, we talked a little bit about that yesterday as well. Sound also needs a medium in order for it to travel. So a wave in general is a repeating disturbance that transfers energy. Really big point there. So as we're thinking about the different times we've seen, heard of waves, let's also thinking about other examples. So a falling pebble is moving, and then that falling pebble has kinetic energy. So here we are mixing in some of the units that we've already learned about. So we learned about kinetic energy last unit. We're talking about how that kinetic energy from a falling pebble then transfers, right? It splashes into a pool and transfers some of that energy nearby into the nearby water molecules, causing them to move. So again, it's this idea of movement, it's energy. We talked about that kinetic energy. There's some momentum here, that transference of momentum, that transfer of energy, that force. These are all things that can connect from things that we've already learned. And then when we talk about those ripple effects, those are just water molecules bumping into other water molecules, causing those water molecules to move. And then there goes that repeating occurrence. So a couple of other things as those molecules pass the energy along to their neighboring water molecules, and then the water itself does not move outward, but the energy is traveling in the form of a wave on the surface of the water. So again, think about this as an example. If you were to put a little water sailboat into the middle and you were to create a wave, that sailboat doesn't move. It kind of sits on top of that water. It might move a little bit, but it kind of stays in the same place as well. So just thinking about that and keeping that in mind, that the energy is moving outward. So, like we said, there are two different types of waves. There is something called a transverse wave. All waves carry energy without transporting matter, right? We talked about that just now. The wave is carrying energy, not necessarily carrying the object. It kind of sits along that wave. Here we have an example of a transverse wave, and this is what we typically think of when we're thinking of a wave. And so you can see this object is moving it up and down, causing this string to move and pass that energy along. In this GIF, it's showing you what that wavelength is. Remember that a wavelength is from peak to peak. It's from one point to the next point in the next starting point. So you can talk about it from peak to peak. You can also look at it from right here to the same spot on the next wave. But that is what we consider one wavelength. Any questions on that? Okay. This is another type of wave. This is called a longitudinal wave. So one thing that I want to kind of pay attention to, this actually moves perpendicular. Okay, so this is moving up and down. This movement is parallel, and this is actually what sound looks like. So sound is a longitudinal wave. So when we are speaking, we're actually sending this energy that is causing the atoms to pulse back and forth. So what they're telling you is, what they're showing you here is these red dots are particles. This is, for example, that matter, that substance that in the earlier slide said that all waves carry energy without transporting matter. And that's what they're talking about here. They're showing you a particle. The particle is not moving away from its spot, but it is moving that energy back and forth. So what we see, these kind of areas of compressions, where the molecules are moving together, that's just meaning that it is moving back and forth between that energy. It's moving that energy back and forth. But then we have this wave. So this wave it's showing you is moving along. Now, when we take a look at a transverse wave, there are other characteristics in this wave. So we know that this wavelength is from there to there. We also have some key vocabulary words like crests, troughs, and then we've got this equilibrium, which we're going to get to in a later slide. But in a longitudinal wave, we have characteristics in a longitudinal wave that are similar to a transverse wave, and that's called compressions and rarefactions. So compressions are those areas where the energy is causing those air molecules to be really close together. So they're compressing together. So this would be a compression. This would be a compression. Rarefaction is that space between the compressions. And that's when there's more space between the molecules and so forth. So we'll get a chance to kind of take a look at this again. But again, this is just a lot of information when it comes to waves. Similar to energy, where we have mechanical energy and electromagnetic energy, we also have those two different types in waves. So mechanical waves, you need a medium in order to travel, so sound or water. In order for sound to travel, there needs to be a substance that the energy travels through. Here we have air. Our voice gets carried by the air molecules around us. Take away those air molecules, you won't have sound. So think about space, where there's no air in space. Have anyone seen the movie Gravity before? Okay, you have, Madeline. So in Gravity, they do a really good job.
I saw it like so long ago, and
it's been a while.
It kind of traumatized me a little bit, but
I can see why. I think I've seen it once and I haven't seen it again. So
yeah, it's like kind of a stressful movie, but
it is, but that's because they use sound a lot. So the funny thing that that movie does is actually just played right into my point. So thank you, Madeline. Could not have had it better set up than that. One of the reasons why it gets really intense is because usually music sets the tone of movies. You can have the exact same scene, but if you have an ominous tone, it's going to bring about a different feeling. If you have a happy tone, it's going to bring about a different feeling. So usually when there's nothing going on, we have some sort of music to tell us how to feel. But in Gravity, what they do is actually show you when there's, because spoiler alert, there are some explosions that happen. And in the movie, they actually show you what it would be like if you were in space during that explosion. So for example, they don't play any sound. You're watching this explosion happen and it gets really intense because there's no sound. And that's exactly what happens in space because there is no substance for that energy to transfer. It's the same thing if you've ever had the experiment, and if we were in the classroom, I would be doing this. We have a vacuum. It's like if you've ever seen those videos or an experiment where they put a ringing alarm clock in this like dome and then they suck the air out, that sound stops producing. That's because there's no medium. Okay, so we also had you guys put the ear on the table by knocking on the desk and notice the difference. That's a different medium, right? So those are considered mechanical waves. Non-mechanical, or what we call electromagnetic waves, do not need a medium to travel. So that's why light is able to travel in space. That's how the light from the sun is able to reach us, even though there's no medium in space, because it doesn't need one. So when we look at this graphic organizer, we have a good way of kind of understanding, right? We've got mechanical waves, which means they need a medium. And then we've got electromagnetic waves, which mean they don't need a medium. So things like light, microwaves, infrared, X-rays, ultraviolet rays, radio waves, they don't need anything to travel through. They just need to travel. But when we come to mechanical waves like sound waves, which is a longitudinal wave, and water waves, which is a transverse wave, that's when we do need some sort of medium or substance in order to travel. How are you guys doing? Do you guys need a little bit more time on this slide, or are we ready to move to the next? More time? No problem.
Okay, I'm ready.
Great. Okay. So, like we said, we talked about this already. What is a medium? It's a substance through which a wave can travel. So water, people, right? When we do the wave at sporting events, that is people is the substance, the medium at which the wave is traveling. Air, coiled wire. Okay, so these are all examples, but they're not, there's still so much more that we can use as an example, but this is just one of them. So, were you writing notes, Abby? I can go back if you were writing. Okay. So what is a mechanical wave? We talked about a wave that requires a medium, so sound and water is going to be big. Like we said, the vibration of an individual air molecule. This is sound, right? So if you've ever seen a speaker, this is another way that you can see that it is a longitudinal wave. is if you put water on top of a speaker, you can actually see the wave patterns that the speaker gives off. But really, the speaker, if you feel it, you can feel the pulse on your hands. It's going back and forth, and it's causing those air molecules to go and shift and move and vibrate back and forth, passing along the sound that we hear, which is pretty cool if you ask me. So this is the sound wave out of your mouth. So this would be the focal point, right? So when we're speaking on our mouths, this is where the source would be, and then it radiates outward, which is exactly what you're seeing here. And it kind of reverberates, right? The energy moves those back and forth, and it kind of gets accentuated from the center outwards, which is exactly what is actually happening in the air around you. Like for me right now, and you guys, for the volume coming through your speakers, it's making the pulses, the energy into the air molecules in your area, in your environment, until it reaches your ear. And then your ear has these little hairs that interpret it and then send those pulses onto your eardrum, which then gets signaled through your brain to create those sounds. So remember that a mechanical wave must have matter to travel through. So what is the medium that these sound waves are traveling through? So here is the sound wave. The dog is barking. What would the medium be for this picture?
Air.
Correct. It is air. Good. Madeline, how are you doing? You're good? You have any questions?
I'm good. No
Awesome.
questions.
Perfect. So let's go ahead and move on to the next. Mechanical waves. So we already talked about this, right? I told you about how there are two types of mechanical waves. There is transverse waves, the one that we often think about that goes up and down. But then we also have these longitudinal waves, which you can see very clearly in a slinky. We always use slinkies when we're talking about waves because they're one of the best ways that we can model it. So longitudinal wave, so a transverse wave, if you had a slinky, you would be the one that's moving your wrist up and down or your arm up and down and causing that wave to go across, right? In a slinky, you would send a longitudinal wave by moving it back and forth, like again, parallel to the ground, right? You would move it like this versus like this. And that's going to cause that compression and that energy to be transferred throughout the slinky. Matter in the medium moves at right angles to the direction that the wave travels. So it's just always moving up and down. And then longitudinal waves are in the medium, moves back and forth along the direction that the wave travels. So really just talking about this motion is going to cause the wave particles to move up and down as they move through. So that's why they're saying that they're perpendicular, right? And then this is moving along the direction. So this is going back and forth. So you see how it's still moving, but it's like the particles are moving in the same direction as the wave is moving. So that is two distinctions between the two. So we've got the direction of wave motion and the direction of the disturbance. The disturbance just meaning the direction that the air particles are moving. So the wave in a longitudinal wave, it is moving. The wave is moving this way, and the direction of the disturbance is also moving in that same way. And then the direction of wave motion, the wave is traveling horizontally, but the disturbance is actually going up and down. So just kind of just really pushing forward that point. Does this make sense so far? Okay. So here is where we start to label. I kind of mentioned this a little bit ago in another slide, but in a transverse wave, we have these things called crests and troughs. So the crests and troughs are the same idea, but they mean different things in regards to being in the positive direction of the equilibrium. So the equilibrium is this baseline. That's kind of what is the middle of the wave. The amplitude, which I just jumped ahead, but the crest here is going to be the top, and then the troughs are on the bottom. So the positive and then the negative along the y-axis of this graph. Crest is the positive, troughs are the bottoms. Again, we've got the wavelength, which is the distance between one point on a wave and the nearest point just like it. This is what I was trying to explain before. You can either choose it just has to be, you can choose any point on the wave, but when you measure it to that same point on the next wave, that is considered one wavelength. So you can either do it from crest to crest, you can do it from trough to trough, or you can do it from this starting point and it would take the entire same thing until the next starting point for the next wave. Okay, so these are 3 ways that you can get the wavelength of a wave. Okay. And then we've got the amplitude, and this is what I was talking about, positive amplitude, negative amplitude. It's the maximum distance the wave vibrates from its rest position. So again, remember this white line here would be the rest position. If there was not moving at all, it would be there. That's what we also call the equilibrium. So the equilibrium and rest is the same thing. They can be interchangeable with rest position and equilibrium. But regardless, the amplitude is the distance, the farthest distance it got from that rest position or equilibrium. The amplitude is going to be the same here as it is here. Okay, so these are going to be the same distances. The only thing that makes this negative is that it just moves, right? Remember that negative values in physics is really just the direction. So if this is positive direction and it moved up, then moving down would then be negative. So again, that negative amplitude is still just representing the direction of travel. The amplitude is a measure of the energy carried by the wave. The more energy a wave carries, the higher the amplitude. And this can be proven if you have done any sort of workout or exercise. They one really big exercise, especially in CrossFit, are those really big those ropes that you kind of stand in this crouch position and you go up and down with the rope. Have you guys ever done that or seen that? You're like seen that?
I've seen it before, yeah.
Yeah. So, you know, if you think about it, it makes sense. And you can even try this at home. If you have some sort of cord or rope and you tie one end down, or not even, you don't even need to have it tied down. You just need to have one end of it. And if I were to tell you, make the biggest amplitude that you can, you're going to start to bring your arm up and down. And actually, it's going to make you expend or use more physical energy. And that's because you're putting that energy into the rope. The rope is the substance. That's the medium that the wave is traveling through when you move it back and forth, or up and down, excuse me. And then the higher the amplitude, the bigger the amplitude, the more energy you have to put in to create that higher amplitude. So the amplitude is the representation of the energy. Okay? So then we have oh, Abby, did you want more time on that slide?
No, I took a picture.
Okay, great. So then we have the relationship between energy and amplitude. No, Millie, don't leave. Thank you. Well, Millie, I'm cuddling her today. High energy waves have high amplitude and low energy waves have low amplitude. So it's pretty straightforward, right? Amplitude, relation to energy. So if we take a look at this picture, we know that the energy is going to be different. Does it have a different wavelength? Is the wavelength changed because of it? Hasn't?
Isn't the wavelength like how long it is, or?
Well, one wavelength. So that's a good question. How many wavelengths are there? How many waves are there?
3?
Yeah. So if there are 3 wavelengths, let me start with this. Has the frequency changed? The amount of wavelengths? The number of wavelengths? No. And so it's safe to also assume that the wavelength has not changed. So that's another thing. Just because you change the energy of the amplitude does not mean that the frequency or the wavelength has changed. It's just that it measures energy. Good. So which one of these has the largest amplitude? A, B, or C?
C.
Good. Yes. And how did you know that, Abby?
I just noticed that the waves seem to be larger than the others.
Okay. Good, good. So the wave seems to be larger. What are you looking at when we talk about amplitude? What are we looking at? Are we looking at from here to here? Are we looking the total from here to here? Or are we looking from the equilibrium to the top of the crest or the bottom of the trough?
I noticed that the equilibrium and the crest, there's like more space in between. Same with the trough and the equilibrium. That's what I noticed.
So I love that you brought that up, Abby. It looks that way, and I think it's really tricky because it's all about perception and how we look at it, right? And how it looks to our eye. But this distance here is actually the same as this distance here. So both of those are going to be the same amplitude, but you were.
Oh yeah, I was saying.
Oh, you were saying that. Okay, great.
Yeah.
Understood you. I apologize.
That's okay. I didn't really explain it.
No, you're great. You're doing a wonderful job. But yes, you are right. C is the one with the largest amplitude, right? Because it has the most space between the crest and the equilibrium, or the trough in the equilibrium. So then which one of these waves has the least energy, the least amount of energy? Madeline, you want to try this one?
A, because not as
And
deep.
how did you say that? Sorry, I interrupted you.
It's not as deep. It's like very like mellow.
Good. Yes. So we can also refer to that distance between the crest and the equilibrium and the distance from the trough. But you're right. It is mellow. It's really like, all right, we're just kind of cruising along here, right? Just kind of doing our own thing. Great. Good job, guys. Okay. Let's go into the next one. So we talked a little bit about the parts of a transverse wave. So now we're going to get into the longitudinal wave, which we've talked about, but I'm going to go into more specific content. Oh, she just has a toy. Okay, this wave is moving in this direction. So it's moving to the right. So similar to a transverse wave where we were talking about the distance of a wavelength is from one point to another, as long as it's the same spot. On the next one, the longitudinal wave we consider from compression to compression is a wavelength. So this compression is that area where the energy is causing the medium or the air molecules to be really, really close together. So they're pretty compressed. Shocking, I know. How did they even come up with these words? And rarefaction, this one I don't actually know how they came up with it, but rarefaction is the less dense area of the wave where the particles are more spread out. There's more distance between those particles. I'm going to let you guys either take a picture of this or draw this down because it is a good thing to have. And I'm going to take a quick water break.
Okay, I just took a picture of it real quick.
Perfect. See, now there's a red-breasted nuthatch. Their cousins must be visiting.
What happened?
Just making a bad biology joke.
Oh.
New bird at my bird feeder at the start of class. So obviously I was telling Abby all about it because she clearly wanted to know. And it was a new bird and I was showing her it.
Yeah, now Abby wants birds.
Yeah. So I'm going to pretend that I had everything to do with that. Okay. Moving on. All right. So again, the way that we call, so remember these pictures are, there's the compression is right here. The rarefactions are those at open, more open. See, there's the white-breasted nuthatch. I'm telling you guys, it's so exciting when new friends come by. Okay.
Abby, just get a bird feeder and trap the bird.
No, never.
Then
We have
he's a
bird
pet.
feeders.
You can't just trap a bird and make it your pet.
Yeah, Madeline, what's wrong with you?
That's
Okay,
not what I'm
don't do that
saying.
then.
Oh my God. Birds are really great, though. I will say they're like the most adorable pet ever. They're really, really social and really loving and snuggly. So, anyway, okay. Don't distract me, ladies. So now it's like on video, it's like literally recording. Anyone can see how to derail me. Great. Anyways, amplitude. The amplitude of a compression wave is related to how tightly the medium is pushed together in the compression. So unlike our transverse wave, where we can actually look at amplitude from the equilibrium to the transverse wave, we look at the density when it comes to the amplitude. So how closely these atoms are. The more energy that's going to be transferring through a longitudinal wave, the more close together those atoms are going to be. And then the wavelength of a longitudinal wave can be measured as the distance between the center of two compressions or rarefactions, which is very similar to a transverse wave. Questions on this? Okay. So we've got that exact, this example again. You've got your wavelength from crest to crest. You can also do wavelength from this point to this point or from trough to trough. It's up to you, but as so long as it's consistent.
What's rest position?
So that rest position is the equilibrium. Those are the interchangeable, those two words. And really it just means that if you were not moving the string or whatever medium you're using, then it would just be at this position. That's like, it's like the OG. It's like the original position. Great. Okay. So which one of these has a larger wavelength?
B?
A.
All right, so you guys both gave me two different answers. So let's talk about why you chose each one. So Abby, which one did you choose?
Oh, there's more space
And which one?
between the two crests.
For A or B?
For B.
Okay. So there's more space between crest and crest. Okay.
The trough is wider.
Okay, good. Madeline, what about you? Which one did you choose?
I choose A because I just think that's because it's longer. It has more string or whatever you call it, wave.
Okay.
But it's
Okay.
still at the same height. It just is more.
Okay. So you actually just touched upon, so both of you guys are noticing something. Now, Madeline, you're actually talking about frequency, which we're going to get to in a second. So the frequency, how many waves there are, A would be the answer, would have a higher frequency. But B has a larger wavelength for the reason that Abby suggested. So Abby mentioned that the distance between crest and crest is larger than this crest and this crest. And that is the difference between the wavelengths. The farther away the crest and crest is from one another, or this point to this point, or this point to this point, the farther it is, the larger the wavelength. Does that make sense? Great. So now, Madeline, we're going to get to frequency. So frequency is the number of wavelengths that passed a fixed point each second. So that's when we're going to take a look at a specific distance and see how many waves pass for each second. Sounds a little confusing, but it's really not. So if we take a look at high frequency versus low frequency, we can start to see, and if we use this X as time, we are looking at how many waves pass through a period of time. One wavelength in one period. So a period just represents the amount of time it takes for one wavelength to pass. Does that make sense? Okay, so here we're going to see that the period is smaller than this period, okay? And there are more waves on this than on this. So we have higher frequency, which makes sense. We're talking about frequency, how often. We have more waves coming through faster, right? Because, oh, yes, got it. Wait, is that a puppy? Is that like a new dog, or is that just a really small dog?
Sorry, I couldn't hear you.
Is that a puppy, or is that just a small dog?
She's small and fuzzy, so she could pass for a puppy.
Oh my God, I love it. Okay, so when frequency increases, that means the wavelength is going to decrease, right? Because if we're going to have more waves in that same amount of time period, that means that there can't take as much space, right? So that frequency is going to be more frequent. You're going to have more of these waves versus having a low frequency, you're going to have less of the waves. So which one of these waves has higher frequency? Madeline?
A, because it's more compacted.
Okay, good. More compacted. We can also say more waves, right?
Yeah.
Good. Abby?
I think it's A because there's more of the squigglies.
Yeah, the waves.
There's more of the waves than there are in B.
Perfect. Yes.
Yeah.
Absolutely. You guys got this. I'm so excited for you guys. This is gonna be really fun. This is like one of my favorite units. I think it's really fun. Okay, so when we're talking about frequency, and so this is going to be where it makes a little bit more sense for your lab, because Madeline, you had asked a specific question about the unit. So here we are with the unit. We call a frequency is measured in a unit called hertz. Okay, so really what a hertz is one wavelength passing by, oh my God, excuse me.
Bless you.
Thank you. My allergies are not great this morning. Okay. So frequency is measured in a unit called hertz. And a hertz is when one wavelength passes by a fixed point per second. Excuse me. So really, it's thinking about one wavelength passing by a fixed point per second. Okay. So now we have the wave equation. So I do want you to be writing this down, because this is going to be a big part of that math representation that we use whenever we're doing problems and trying to solve solutions. So the velocity of a wave is equal to the wavelength times the frequency, which makes sense, because if we're thinking about the equation for velocity for like a car, we think of that as distance times time. Can you guys hear me? Okay. I was getting
I'm just writing it down.
Okay, no, I was getting a notification that said I had to turn on my microphone. I was like, I swear I did.
Oh.
As long as you guys can hear me, that's what matters. So thinking about velocity of a car, for example, as distance times time, that's going to make sense for wavelength times frequency. right? Because wavelength is the same as distance. Frequency is that time factor. Okay, now I messed up. Velocity is equal to distance over time. Frequency is 1 divided by time, which is why we multiply it. That was more for me than it is for you, so just ignore everything I said. But this is the equation. So velocity, or how fast the wave is traveling, which we use this unit for meters per time per second. Lambda is this weird little Greek letter. We really like using Greek letters in math to represent specific variables. So lambda just represents the wavelength. Okay, so we usually, it's like this little letter. You can just draw it exactly like you see it. The wavelength, and that is the unit is meters, and then the F represents frequency, and that unit is hertz. Okay, so write this down, take a picture, and then let me know when you're ready to move on.
I have a picture.
What's that, Abby? You ready?
Yeah, I have a picture of it.
Okay, perfect. Okay, so let's just do a little review. We've got, what kind of wave is this, first of all? What wave is this? Do you guys remember?
Transverse.
You got it. It is exactly. It is a transverse wave. Remember, the trough is that point from the equilibrium from the bottom. The crest is that top point. We've got the amplitude, which is the distance between the equilibrium or rest position to the top of the crest, and it's also the same to the bottom of the trough. And then we've got our rest position or equilibrium. Remember, those two terms are interchangeable, but that would be the place where if you were not putting any energy into it, it would just be rested right there. Couple of things to remember. A wave is a repeating disturbance or movement that transfers energy through matter or space. Waves carry energy. Mechanical waves need a medium through which to travel. We said that. The two types of mechanical waves are transverse and compression waves. Parts of a transverse wave are crests and troughs. Parts of a compression wave are compressions and rarefactions. Amplitude is how much energy the wave carries. The more energy, the higher the amplitude. Wavelength is the distance between a point on a wave and the nearest point just like it. Frequency is the number of wavelengths that pass a fixed point each second. As frequency increases, wavelength decreases, and wave speed is equal to wavelength times frequency. Now we've got some time for practice. Are there any questions so far before we get to practicing?
No.
Okay. Abby, any questions for you? Perfect. All right. So we're going to do a practice problem from our book, page 166. So I've got that equation up there for you just in case you need a reminder. But per usual, let's go ahead. If you would like to take a picture of this practice problem or open up your book to page 166, because I'm going to turn on the whiteboard feature so we can do this problem together. But before I do that, as always, we're always going to look at our givens. We're going to figure out what we're solving for or our unknown, the equation that we're going to use, and then the answer to our question. So radio waves are transverse waves that travel at a speed of 3 times 10 to the 8th meters per second. K-Love is a radio station that broadcasts at a frequency of 90.7 megahertz. What is the wavelength of the radio waves transmitted by K-Love? Note 1 megahertz is equal to 3 times 10 to the 6th hertz. So let's go ahead and get to our whiteboard. Oh my gosh, I forgot we've done so much. Okay, so we first are going to write down our givens. So what information was given to us in that problem? You guys
By the
remember?
way, your handwriting has gotten so much better on the whiteboard than when we first started.
Thank you. I feel really proud about that. I feel like I've really practiced too much.
I mean, did you get like a stylus for it? Because before it was
No.
like you're using your mouse and it was so bad I could barely read it. But now it's like better.
No, I just think I got used to it. And I do think last time there was some weird calibration going on. And I think maybe that bug got fixed. But thank you, Madeline.
You're welcome.
Progress and growth. I appreciate it. Okay, so do you guys remember the information that was given to us? What information do we know from our problem?
It's on 166, right?
Correct.
Okay. So the velocity is
Mhm.
3.00 times 10 to the power of 8 meters per second.
Good. So we know the velocity. What else do we know?
The frequency
Good.
is 90.7 MHz.
Yep, and that stands for megahertz.
Oh.
Great. And anything else? We just want, yeah.
We need
No,
to
go
find
ahead,
the
go ahead.
wavelength.
Good. So we are solving, right? So our unknown is lambda, right? That unknown. That's how I draw my lambda. Okay, so we don't know lambda. What equation are we going to be using for this?
Velocity equals lambda times frequency. But like not
Good.
in that order.
Yeah, no, you got it. Velocity is equal to frequency times lambda, or lambda times frequency. Remember, it's multiplication, so the order doesn't really matter. Millie, enough. Millie, Millie. My dog doesn't listen. I'm ready to throw something at her. Hold on.
Okay, Miss Fierstein. I hate to take this back, but the handwriting has gotten worse. The given is great, but like I can't read the last part you just wrote.
I can read it to you. It says equation equals
Okay.
v times equals frequency times lambda. It's not that
Still
bad.
good though. Don't
Please
worry
zoom
about
out.
it. It's still good, okay?
No,
Oh my
please
God,
zoom
you
out.
guys are so funny. It's funny because I was actually thinking that to myself. I'm like, great, she jinxed it in my head. Read that again. It's okay. It's okay. Now, I'm not going to take offense to that. I still feel like this is still growth from the beginning of the
It
year.
is, definitely.
Okay, so we know our equation. So we do, however, have pointed out that we are solving for lambda, which is this right here. So how are we going to rearrange this equation so that we can solve for lambda? What are we going to do? How do we rearrange this equation so that we get lambda by itself?
Lambda equals velocity divided by frequency.
You got it. Yep, that's absolutely correct. Yep, because you notice that there's a multiplication right here, right? So in order to get lambda by itself, we have to do the opposite. So we're going to divide both sides by frequency, right? We're going to have to divide both sides by frequency. This frequency cancels out, and that leaves us with lambda on its own, and then velocity divided by frequency. Great job. So now let's go into solving our unknown. So what is our solution? So we have some information, right? Oh, see, Madeline, I got too confident. Okay, let me try.
Okay, your handwriting is awful. All right, it's not even good. Okay,
Is this reverse psychology now?
I'm trying to unjinx it.
Unjinx.
Okay, that was
think that's
so
not
bad,
right.
so bad. All right,
It actually did get better though.
it
All right,
did.
we're just gonna start doing this. Like, let's just start doing like experimental things during lessons now too.
Okay. Actually, it did not get better, Abby. It did not. It's not getting better.
So if we use this equation and we're gonna solve for lambda, what numbers am I gonna be putting in for what? So we know that lambda is what we're solving for. So what do I put in for my v? What do I put in for my f?
I was gonna say something, but it didn't come out.
Oh.
Velocity, which is
Yeah.
3.00 times 10 to the power of 8 over frequency, which is 9d.7. But how do you divide that?
You're just gonna have to write it into the calculator appropriately. Wait, hold on. I lied. Did I lie? Yes, I did. Okay. Well, not yet. I didn't lie. Actually, I did not lie. However, we do need to do one more thing before we can finish this problem, which I almost forgot. And that's the fact that we need to change this to just hertz. So we need to convert this so that it's just hertz down here, okay? So the way that we do that is, let me change the color here. We have 1 megahertz is equal to 3 times 10 to the 6th hertz. So if 1 megahertz is equals to 3 times 10 to the 6th, then we need to do what to this? We're going to need to divide or multiply to convert this.
Divide?
Correct. So I'm going to do another 90.7. Right? Remember that when we do conversions, we said this is on the bottom. Okay, so then maybe I was wrong. We're not going to divide. We're going to multiply. Right? So whatever you're, like if you're not sure, just go ahead and write out the math problem. Remembering that this megahertz is going to cross off this, you always want to have the same unit diagonal from each other. And then you're going to go ahead and multiply across.
I gotta go. I'm really sorry.
That's all right. No worries. We'll
Not
pick up
on
on this
technology.
in small group, okay? Well, actually, class is over and I have another class to go to. So let's pick up here in small group and then we can also work through the lab after we're done with these slides, okay?
Okay.
All right.
Thank you.
Thank you so much for joining me. Have a wonderful day.
Bye.
Bye.
Okay.